Hi, class. This is Mr. Hart. I just am making this podcast to go over some of the things we talked about in week 2 of the motion unit. So, the first thing we talked about is we wanted to discuss the idea of acceleration. So, if you think about acceleration, it is a change in speed or direction, or in other words, a change in velocity. So, for example, if you are thinking about your car, right, when you press in on the gas pedal, they call it the accelerator because it changes your speed. Okay, it changes the speed of the car. So it is getting faster and faster and faster. That's acceleration. Okay. So another example is think about racers at the starting blocks, right? They undergo a massive change in acceleration. They start from 0 miles per hour or meters per second, and they go up to 10 meters per second. Okay. So their change in speed is very dramatic. So they accelerate very fast. Okay, another example is a change in direction. This one's a little more counterintuitive. Okay, but imagine there's a runner right here, and he runs and he runs and he runs. Okay, and he goes around this curve. Okay, so even if he's going a constant speed around this curve, he's still accelerating because he's changing directions. Okay, excuse me. And that just comes from the definition of velocity because velocity is dependent on direction as well as speed. When we change direction, we're also changing velocity. Okay, so that's an acceleration. Okay, so the mathematical definition of acceleration is acceleration A equals the change in velocity over the change in time. Okay, very similar to the velocity equation, right? So anytime we need to calculate acceleration, we just find our change in speed divided by our change in time. Okay, so let's look at this example problem. Okay, so for example, if a sports car goes from 0 to 60 miles per hour in 5 seconds, okay, then we want to find its acceleration. All we have to do is we find its change in speed. Okay, so its change in speed or change in velocity was 0 to 60, okay, or 60 miles per hour. Okay, our change in time was 5 seconds. And so if we're finding acceleration, we just divide those two. Okay, so our acceleration is 60 over 5, or which would be 12. Okay, 60 over 5, or 12 miles per hour per second. Okay, so if we look at these units, they're kind of strange. Okay, they're not miles per hour or meters per second. It's miles per hour per second. But that still makes sense if you think about it, because miles per hour is the speed. Okay, and we're increasing by 12 miles per hour every second. Okay, so we're changing our velocity, miles per hour per second. So it's kind of a strange unit in this case because we have 3 different divisions. Okay, if we were doing meters per second for this example, okay, then our unit would be 12 meters per second per second. Okay, so changing 12 meters per second every second is the same as 12 meters per second per second. Okay, so again, really strange unit. And usually how they write it is if we have this meters per second, they'll actually do the mathematical concept of bringing this up here. So it's meters over seconds times seconds. And so what we end up with is meters per second squared. Okay, so when we talk acceleration, you'll often see it written like this, meters per second squared. But the intuitive way to think about it is it's the number of meters per second that we're changing per second, or meters per second per second. So whenever you see this, think of that. Okay, hopefully that makes some sense. Okay, so if we look again at the acceleration equation, okay, we can rearrange it. Okay, if we modify this equation, okay, we can rearrange it. So we take our normal equation, A equals change in V, over change in t, and we end up with, by timesing this t over here, right? Instead of t being divided, we times it to the other side, okay? So we get acceleration times change in time equals change in velocity, okay? And then if we write the definition of change in velocity as v final minus v initial, okay, then we get acceleration equals change in time equals final velocity minus initial velocity, okay? And then if we add this initial velocity over to the other side, we get one of our other equations, okay? So this equation says that the final velocity is equal to the initial velocity plus the acceleration times the change in time, okay? So again, it's just a simple modification from the acceleration equation that we get this. Okay, final velocity equals initial velocity plus acceleration times change in time. Okay, so I'll go ahead and let you do this one. So if you're doing participation, try to answer this one on your paper. Okay, a parked car accelerates at 8 meters per second. Sorry, and that's supposed to say meters per second squared. Okay, a parked car accelerates at 8 meters per second squared for 12 seconds. What is its final velocity? So use that equation we just saw and try to figure that out. Okay? Alright, so then we looked at the last two equations. Okay, so by this point you know all the terms, right? So these are just other modifications that we can see from the other equations. If we just do some simple modifications, you can get these ones. So they're just other useful equations for kinematics problems. Okay, so change in position equals 1/2 v initial plus v final times t, or the change in time. And the change in position also equals the initial velocity times t plus 1/2 the acceleration times t squared. Okay, so for any physics problem, again, you can look at that paper on how to solve physics problems, and it will help you figure out which type of equation you need to solve a specific problem. Okay, you find the variables you have, find which equation uses them, and you can solve for the quantities you need. Okay, so hopefully by now on your class notes you should have all the equations understood and defined. Okay, well, this is the cool thing about kinematics. If you look at all those equations that we have, okay, they kind of have a specific relationship, which we call this, I like to call this ladder. Okay, so we started with a very simple equation of position, what it is, right? So it's a change in position is the final position minus the initial position. Okay, simple enough. That was our first equation. So I call that the top rung of the ladder. Okay. Then if you look at velocity, one rung down, then all you got to do is you got to take the position divided by time. Okay, that gives you the velocity. If you want to go another rung down to acceleration, you just take the position divided by velocity, take the velocity divided by time. Okay, so every time you go down the ladder, you're just dividing by time. Okay, very interesting. And then when you go back up the ladder, you're timesing by time, but we also do some simple modifications to it, and we end up with these equations. Okay, excuse me. So this is interesting. This is cool because for whatever thing we're looking for, if we're looking for acceleration, we're looking for velocity, if we look for position, we can climb the ladder or go down the ladder by using these equations. That's what helps us find these different quantities. Okay? And then the last equation, this change in x equals vit plus 1/2 at squared, this one is a direct jump from acceleration to position. So if you need to do a double jump across velocity, you use that last equation. Or if you need to do a double jump down, you can also use that last equation. Okay, so we can get from any position on the ladder to any other position on the ladder through these kinematic equations. So this is really cool. This is nice. It really helps us out with solving these different problems. Okay. Then we, so after this we did a simple activity to calculate acceleration, and we did this activity about car brakes, seeing how quickly you could brake a car. So I would recommend having you try this to see if you can figure out how long it would take these cars to brake. But we did it in class, and we found out that we have this this quadratic pattern. Okay, so the farther and farther your faster and faster you're traveling, the farther it will take you to stop. Okay, because you're going faster, it will take more to slow you to a stop. So if you're going 20 miles per hour, it takes you 12 meters to stop. If you're going 30 miles per hour, it takes you 23, 36, 53, 73, 96. It gets harder and harder to stop, right? It's taking you more and more distance to stop. Okay, so this comes straight out of the kinematic equations. So very interesting. And last of all, we talked about the free fall equation. Okay, so the free fall equation is just a specific version of this equation down here. Okay, if we cancel out the VI, okay, set this term to 0, and we replace A with G, and X with Y, we get the free fall equation. So what this is saying is we use Y to represent height. So the height of an object is equal to 1/2 the gravitational acceleration times the time squared. So for example, if I had a person on a ledge, okay, here's the person, okay, and they drop a, whatever is a ball off the cliff, okay, and let's say it takes, 3 seconds to fall to the bottom, then we can use this equation to tell us how tall this cliff was, okay, because we know the gravitational acceleration, we know the time, we can figure out the height, okay. So this is a really useful equation because this is for any type of falling motion from gravity, okay. And just so you know, G, okay, the gravitational acceleration equals 9.8, and I apologize for my bad handwriting, meters per second squared. Okay, so 9.8 meters per second squared. Okay, this is constant for wherever you're at on Earth. This is pretty much the same. Okay, so if I'm on this cliff and I time it for 3 seconds, I know I can plug this into this equation, put in 3 seconds in for here, 9.8 for there, and I can get my height. Why? Okay, it can tell me how high this cliff is, which is pretty cool because all I need is one thing, the time. So if I have the time, I can calculate the height of the cliff. Okay, so pretty cool. So try this problem if you're making a participation. Okay, so if you're a cliff diver or you see a cliff diver and he jumps off a cliff and it takes him 4 seconds to hit the water, how tall is the cliff? Okay, so use that equation, plug in G, plug in the time, and figure out the height. Okay? Awesome. So the other cool thing is with this equation is you can go both ways. So for example, I had a real life story where I was at a neighborhood party and a man was shooting potatoes into the sky with a potato cannon. Don't ask me why he was doing it. I have no idea. But anyways, he was wondering how high the potatoes were going. And since I was a physics teacher, I was like, hey, I know how to do this. Let me help you out. So I got my timer on the cell phone, okay, and timed how long it took to come out of the cannon and hit the ground. Okay, so we can use the free fall equation to do this, even though it's not free fall. He's shooting it up into the air, right? So what you'd have to do, though, is it's very simple. If he's down here and he shoots the potato up into the sky and comes back down, okay, half the time it's going to be going up, and the other half it's going to be going down. Okay, so this is really nice because we can still use this free fall equation. Okay, all we have to do is before we plug in our time, we just divide it in half. So let's say it took 5 seconds for that potato to hit the ground. All I'd have to do is put in 2.5 instead of 5, and I can still figure out how high the potato went. Okay, so for non-free fall, for shooting something into the sky, you can still figure it out. You just plug in half the time. Okay. Then lastly, we watched this cool video about where bullets go if you shoot them up in the sky. It kind of talks about the same thing of how they'll come back down with the free fall equation, and they'll come back down with the same speed that they were shot up. So if you want to watch that, go to this web address. Okay, but that's all we talked about for this week, and hopefully that makes sense. If you have any questions, let me know, and thank you for watching.